So we spent a bit of time going over the notation for pointers, the syntax, pointer arithmetic, etc. But what are the main application of pointer that we've seen so far? Well, we can use them to navigate the contents of an array. Okay, we can use them as a way to reference a subpart of the array. For example, everything from the third element up to the end. We've seen that they are essential to enable us to pass parameters by reference, even though we understand that there's no such thing as passing by reference. Really, it's just passing by value, something that is a memory address, a value that is a memory address. Um, and I'm going to add one more application. So this application is not actually in our current reading assignment from the textbook. Okay, the textbook introduces it later. I prefer to introduce it right now because that way we have more time for you to practice with it during the semester. Because it's a very powerful technique, but it's also something that requires practice so that you get it right and you don't introduce a ton of bug every time you try to do it. So what is this? Because I keep talking about it, and it's not getting clearer what it is that I am trying to introduce. So it's dynamical memory allocation. So unlike other languages like Python and Java, and many other modern language actually, that allow you to allocate dynamically memory for some objects, for example. See the keyword new, for example, in Java. Um, those languages allow you to allocate memory, but never worry about deallocating it. You say, I want more memory to store this object. Okay, here you are. I want more memory. Here you are. And then you never worry about freeing it. In C, and in other language like Objective-C, for example, the situation is a little different. The memory management is what we call explicit. It's completely in the hands of the programmer. He or she can decide when they want additional memory to be allocated for objects and structures and stuff like that. And they have to decide when that memory must be deallocated. So with great responsibilities, etc., etc. Okay, with great powers there comes great responsibilities. The idea is you are in charge of doing those allocation of memory and their deallocation, and if you mess that up, you are going to introduce a new kind of bug. So let's take a look at the syntax. Let's take a look at what this entails, and let's try to write our first bugs. So we know how to declare a pointer. Here's a pointer p, pointer on int. So now it's pointing to nothing. So it's initialized to null. What I'm going to do is, instead of having a variable of type int and then make my pointer refer to that variable, or instead of having an array of a bunch of int and making the pointer refer to one of the arrays inside, one of the elements inside the array, okay? What I want to do now is I want to create a completely new variable of type int, if you will. As a matter of fact, I don't create a variable. What I create really is I reserve a space in memory that's big enough to contain an int, and I'm going to put its address in my pointer. And therefore, every time I dereference the pointer, I can read or write an int at that location. And if I create another one, well, yeah, it's kind of like equivalent to creating a variable, but these spaces in memory don't have a name. I refer to them just with their memory address via dereferencing a pointer. So how do I do this? Well, there is this function called Malloc. Malloc, memory allocation, allows me to say, I want this many bytes. It's very low level, right? It doesn't say like in some languages, you say, I want to create a new object of class, employee record or something like that. No, here in C, we are much lower level. We say with Malloc, I want to allocate this many bytes of memory. So what do we use when we want to measure the size of something? We use the size-of operator. So malloc and size-of are going to work hand in hand together. For example, if I say I want to allocate memory, and the quantity of memory I want to allocate is the size of an int variable, so this is going to give me the number of bytes that I need to store an int variable. And it's going to put that memory address inside of P so that I may then access it by dereferencing P. one more thing I need to do, if I have a pointer on int, because Malloc is very low level and is completely blind to what we're trying to do, Malloc just says, tell me how many bytes you need, and I'll get that for you, right? So I give it a number of bytes here, but I need to also convert to an explicit typecasting here on the return value, which is an address, and which is actually a void star, a pointer on void, right? Remember, we talked about those, and I told you that they would come back to haunt us. Well, there they are. Malloc returns to us a pointer on void, which is actually not really a usable pointer. It's a memory address, sure, but it's not meant to be dereferenced. Well, to allow me to dereference it, I'm going to say convert that pointer on void into a pointer on int, so that I may then assign it to a variable that is also a pointer on int. And when I dereference it to read or write at that memory address, I'm going to read or write one int at a time. Okay, so the formula is not too complicated. Okay, now I'll give it to you. Allocating one variable like that is a little odd, but we're going to start with that, and then we're going to do stuff that is much more useful very quick. Okay, but now I can dereference. I can say there's a new memory zone that can hold an int value is going to contain the value 42. And I can do printf and tell everyone that at this memory address, star p, we have the value 42 being stored. So I use star p to write a value here. I use star p to read the value that I previously wrote. I don't need data. That was all kind of stuff I was doing. Okay, I allocated my new int storage, and I used it both for reading and writing. So let's compile. Let's run it. Star p is 42. That works. Okay. So the thing to understand is that there is another difference between this and regular variables. Regular variables, they are allocated on the stack. Okay, the program's execution stack in the activation record of the function in which they appear. Well, when you do malloc, the memory doesn't come from the stack. It comes from another area of memory called the heap. And this gives us interesting properties. Let me show you. Here, I'm going to say I want a little method called something. Actually, you know what? I'm going to say it returns a pointer, and it takes, say nothing. I don't need it to take anything really. And what I'm going to do, I'm going to create my pointer and put a value in it inside the method something. And then I'm going to return p. So I return the address that I just allocated, okay? And inside the main, I'm going to say int star ptr. Here's another pointer, also starting at null. And this other pointer is going to be equal to calling the method something and having it return the address of the pointer of the memory that was allocated here. So that means what? That means that I allocate some memory inside the method something. Well, yes, sure. I allocate memory on the activation record for the variable p, the local variable p. But that memory will disappear once I return from my function. On the other hand, any piece of memory that I allocate explicitly using malloc is going to survive the end of the function. So after the function is over, I return that address to the caller, the main, and the main is going to be able to still continue to access that memory address because it still exists, it's still available. So from the main, star ptr is, and we're going to display the value that is there, star ptr. And I can read it, I could write it, I could change it, of course. Okay, this is not a problem. I can use it because this memory address still exists. So let's run that, and then we'll do a little stack diagram to show exactly what's happening. So I forgot again my prototype here. I've been spoiled by other programming language for too long now. Int star something. There we go. Let's get rid of this, and then we'll see the other errors. Implicit declaration of print. Well, that's just plain silly, not to say another word. This is an F that's missing. What else you got? Nothing? Okay, let's go. So start P is 42 from the main, start PTR is 42. So here's what happened. And we're going to trace that with a blank piece of a whiteboard here, paper. All right. So what happens here is we have the program's execution stack here. All right. We have the activation record for the main method, the main function, sorry. Inside of it, we have some system information here. We don't care about this too much in this course, okay? Then I have a local variable named PTR that contains null originally, and then I assign to it the result of calling the function something on line 11. So when I call the function something, here's the activation record for the function something. It's going to be pushed onto the stack. Inside the function something, again, I have some system level information that I'm going to skip over in this course. And then I have a local variable P, okay, that contains null. So PTR contains nulls initially, P contains null initially. And then I call Malloc on line 22. And Malloc is going to go to a different area of memory. So this here is the stack, okay? And it's growing as we use more and more of it upward. Well, there is another area of memory which we're going to call the heap, and actually I represent them upside down here in this diagram, but that doesn't matter. We're just focusing on the concept here. There is another area of memory called the heap, and in the heap, this is where we are going to carve out some memory when we call malloc. So let's say that we have already a bunch of stuff allocated in the heap here. When I call malloc on line 22, it's going to carve out a space big enough to contain an int value. And that memory is actually now reserved to my usage. It's no longer free for the system to use for whatever it needs, okay? So I booked this piece of memory, and I'm referring to it with a certain memory address. So let's say that it's located at memory address alpha, okay? I'm referring to it with the pointer P, in which I store this memory address alpha, okay? So now that I did that, now my pointer P, we say that it points to that memory address, that new element of type int. Line 23, start P equal 42, I take P and its memory address, I dereference P, so I go to this memory address and I write 43 inside this space, knowing that 42, not 43, knowing that this is an int value, so I encode it with zeros and ones just like I encode any int value, and I write it inside this newly allocated zone of memory. Then line 24, I display star P, which on the screen is going to give me a nice 42, and I return P, so I return this address. The address alpha is going to be returned to whoever called the function, so that's the main on line 11, and the main is going to assign this alpha to PTR. So PTR ends up with the value alpha in it. And when I'm done with this method, with this function, well, all of this, the activation record corresponding to the call to the function something, is removed from the stack. And we are back on line 11, assigning the value alpha to PTR. And then inside the main, we can say now that PTR points to this area of memory as well. So when I do star PTR inside the printf on line 12, I take PTR, I take the memory address inside of PTR, dereference it, go at that memory address, and I find an int value, 42, which is what I display with my printf. So you see that everything that is allocated in the heap persists. Persist until what? Well, persist until you get rid of it. So that means that at some point in time, we are going to use another function called free, okay? And I'm going to say I want to free whatever has been allocated at address PTR, and only when I execute this zone of memory here is going to be deallocated. Okay, but I have to do it explicitly. Hence the term, explicit memory allocation. I decide when the memory is allocated. I decide when it's no longer useful, and therefore I try to free it. And after freeing it like this, if I try to use it again, for example, I do star ptr equal 9,999, okay? Well, this is a problem because now I said I don't need any more this memory. So officially, I'm not allowed to use the memory anymore, but I'm still trying to write at that memory. And you will observe that the compiler lets me compile this, and the runtime doesn't even crash. So that means that there is very little that is done by default in the C language to ensure that you are not using memory that doesn't belong to you. Okay, so that's why it's all on you, the programmer, and you have to be careful that every time you allocate, you deallocate the memory, and every time you use a pointer to dereference that pointer and access some memory address somewhere, you have to make sure that the value inside the pointer is legitimate. Because again, the compiler is going to be able to do very little to help you. There are other tools. I'm going to introduce some in the extra readings for this module, extra material, right? But they are optional in the context of this class. In the context of this class, what we are trying to achieve is to make you rigorous enough when you program with the C language that you can actually write correct code even when manipulating things that are potentially dangerous, like pointers. Okay, this is why I often tell my students that it doesn't matter if you're going to use the C language a lot later in your career. Spending one semester programming in C, learning to pay attention to all those details, etc., is going to make you a better programmer, in my opinion, period, no matter what language you end up using afterward. So, what we have here, we have our pointer on one variable. So I'm going to remove this line because this is actually a bug, actually, even though the program doesn't crash. I have the pointer that is allocated in a function. The function returns the address, and then I deallocate it using the free function when I don't need it anymore. So, what else can we do? We can illustrate with a simple program like that. We can already illustrate memory leaks. Memory leaks is when you forget to free your memory. And if I forget to free my memory here, not much is happening. Okay, it looks like it's still working. Okay, well, let's cause it to actually show us that there is a problem. What if I have a loop that runs for a long time, and this loop is going to be an infinite loop, okay? So you cannot be more, you cannot run any longer than infinity, right? So I have a while true loop. That means the condition for continuation is always true. This loop is going to keep going. And every iteration, this loop is actually calling the function something. And that function something, the interesting part about it is that every time you call it, it allocates a new chunk of memory in the heap to contain a single int. So we are allocate just a little bit of memory every time, but we keep coding, and we keep actually accumulating the memory that we allocate like this without ever freeing it. Okay, that's the important point. So let me try to run this. You're going to see what happened. So it compiled just fine. Actually, it compiled just fine, especially that I didn't save my file. So let's try again. There we go. It compiled just fine. I run it. It's going to display, what is it displaying? Yes, it's displaying P, star P is 42 inside the function. So every time the function is called, it's displaying that little message on the screen. And we keep coding it, keep coding it, keep coding it. The fact that we display something on the screen is going to slow down things tremendously. So let me try to comment this out, and we are going to recompile it, rerun it, because eventually it's going to crash here. But it's going to take already a little bit of time to show you that. And if, so Control C to stop the execution. And if I display something every time, it's going to take even longer. So let's try again. Out. So I'm going to let it run in the background. And it's doing the same thing. It's just silent, okay, not displaying anything on the screen. So it's taking less time to make each iteration. And it's allocating memory, allocating memory, allocating memory until it runs out of memory. And when it runs out of memory and tries to allocate a little bit more memory, the operating system is going to kill the process in which a program is executing. This is a safety so that the whole computer doesn't go down, okay? Because we don't have any memory to do anything anymore. This process was going rogue, was accumulating memory without ever freeing it afterward. While the operating system, after a while, said, "I've had enough. That's as much memory as you're going to get from me," and now I shut down the program. So I didn't stop the execution. My hands were on the keyboard. I didn't use Control C, right? But it still stopped the execution of my program. The operating system did that for me. Okay, so that's the example of a memory leak. Does it matter? When you write a program that's going to run for 5 seconds and allocate maybe, I don't know, 2 megabytes of data total, and then shut down, it doesn't really matter. I'm putting air quotes here everywhere. Okay, every single word has air quotes around it. It doesn't really matter in the sense of you can be as sloppy as you want in your code. You are not going to break anything. That's what I mean by it doesn't matter. Now, does it matter that you are being sloppy when you write your code? Yes, it does. You should be a good programmer. You should not be a bad programmer. So you allocate memory, you never deallocate it, but nobody notices. Okay, maybe somebody is going to audit the system and realize that your process seems to be like hugging, a lot of memory, but that's it. It's still working, it completes, it executes, does its job, so everything is shiny captain. Well, when you write a program that is meant to run for more than a small duration, for example, something that's going to run in the background 24/7, like a microservice, a server-side component, or something like that, then you don't have this luxury of the program terminating. And when the program terminates, the operating system deallocates all the memory that you allocated during your lifetime for you. So you don't have this luxury. You don't have this big cleanup done by the operating system for free. So your program keeps running, keeps accumulating memory that it allocates, and never, ever releases it. And after a while, even if you are leaking it's called a memory leak, even if you are leaking only a little bit of memory every few minutes, eventually it will add up, And your program using a lot of memory means that, your system is going to start maybe swapping, things like that. You're going to observe deterioration of performance. And at the end of the day, at some point, the performance is going to be really, really bad. You're going to say, I need to reboot the server. Or you are going to even kill your process, and your server-side process or your service is going to crash. Okay, so what I'm trying to tell you here is that good programming practice avoid memory leak. Good programmers avoid memory leak. So if you have a memory leak, it's considered a bug. Actually, it's considered a mistake. There's no such thing as telling your boss, we need to reboot the server every Tuesday. Just so that everything works for like an entire week. But if we keep the server up for 2 weeks in a row, then suddenly everything becomes sluggish. That's not a solution. Rebooting the server to clean up, the memory that your process are leaking is not a solution. The solution is to actually inspect the code, find those memory leaks, and remove them. How do you remove a memory leak? Well, you make sure that as soon as you don't need the memory anymore, you free it. So for example, here, we're going to do a little experiment here real quick. I'm going to keep this like this, and I'm going to simply run a.out, but with the time command, okay? I want to see how long it takes pretty much before the operating system shuts down my process because it's leaking memory. So, okay, it took about 9 seconds. So let's say 10 seconds clock time. Now, what I'm going to do is every time I allocate like that, I'm going to deallocate immediately after, okay? And we're going to count to 10 together, and we're going to see that the program is not going to crash. So here we go. 1, 2, 3, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7, 8, 9, 10, 11, 12, 13, 14, 15. It keeps going. It keeps going. Why? Because every time I allocate, I also deallocate. So I'm going to shut it down by hand. I'm going to use Control C, okay? But this program has been running. We know that it cannot run more than 10 seconds, okay, if I waste memory at every iteration. It has been running for 26 seconds without any problem. So try to scale up that in your imagination, right? You are writing a server-side component. If you have a memory leak every week, every 2 weeks, every month, maybe if you are lucky, you are going to have to reboot your server because the performance degrades tremendously. It runs pretty much out of memory. It starts swapping and stuff like that. But if you write your code correctly, you can run it almost, forever without any problem. So that's the value of good code. And other programming language tend to make the programmers forget about things like that. Well, that's the job of the C programming language. The job of the C programming language is to expose to you for one semester all of those low-level concerns so that you may be aware of what's happening and aware of things like memory leak, etc. And therefore, that makes you a better programmer. So we have been doing a lot of stuff here allocating a single int. Well, let's do something a little bit more interesting now. So I'm going to go back here. And I'm going to remove that while loop. There we go. And I'm going to put the free at the end. There we go. And I don't know if I'm going to keep that. Yeah, probably in one form or another. So I'm going to still have my little function create some dynamically allocated memory. But this time what I want to do is I want to allocate an array of int. So allocate array of int. And you're going to tell me the size of the array that you want. Okay? So let's go allocate array of int and int for the size. There we go. And how do I allocate dynamically an array? How do I allocate more than one int at a time? Well, remember when I told you that Malloc was totally blind and it didn't care at all about what we're trying to do. It only cared about one simple question: how much memory do you want? So if I say is Malloc size of int, that means allocate a piece of memory that is big enough to contain one int. Well, if I want to allocate a dynamical array of, let's say, 4 int, then I would multiply the size of int by 4. Therefore, Malloc would actually find a chunk of memory in the heap that's big enough to contain 4 ints, one after the other, and 4 int that are one after the other in memory. If you give me the address of the first one, I can treat that as an array, right? We've seen that in previous video. So this is exactly what we're going to do. So inside the main, again, same thing, because it has been allocated on the heap, I can use it after the return of the function. Inside of the main here, I can use indexing notation here to say the first element is going to be 1, the second element is going to be 2, and so on and so forth. I cannot type, sorry about that. Equal 3, and ptr index 3 equals 4. And of course, I have to be careful, okay? If I call the method allocate array of int, allocate array of int, and I say I want an array of size 4, right? Then I'm going to create dynamically an array of size 4, return the address of the first element, and then it's up to me to remember that this is size 4, so I can only access element from index 0, 1, 2, up to index 3. Okay, so those things I need to keep track of separately by myself, okay, generally with constant and stuff like that. But other than that, this is a syntax. It's not much of a jump once you know how to allocate one int to be able to allocate a dynamically sized array of as many int as you want. And we call them dynamically sized because you can know the size that you want at runtime if you want. Okay, for example, you can say here, printf, how big of an array do you want, scanf the size of the array, and then pass the size as parameter here to the function call. That's no problem at all. Okay, let's try to compile this. Let's run it just to make sure that the code is not full of bugs. There we go. And I don't need to time it this time. So from the main, star PTR is 1, so that's the first element, yeah. And if I say PTR index 4, well, 4, no, that would be a problem. Index 3, there we go. That should give me the value 4. Okay. So the interesting thing about that is PTR contains the address of the first element. So when I do free PTR, here's an open question for you. How does it know to deallocate 1 int in this case or 4 int? Because the address inside PTR, whether I allocated 1 int or 2 int or 3 int or 4 int or a million ints here, what I get out of this function is the address of the first one. So how does it know that it's going to have to deallocate a bigger chunk? Okay, well, this is part of the bookkeeping that is kept by the memory allocator. So Malloc, Free, if they work together, they have data structures that help them keep track not only of the memory address where you allocated something, but also the size that has been allocated there. And when you deallocate, this is how it knows exactly how much it's going to have to deallocate. All right. Now, we have been talking a lot about array of int. That's a general thing that I do in those lectures. I use int as a base example, and then we can generalize to arrays of double, arrays of char, arrays of float, arrays of whatever over data type you want, okay? What about arrays of chars? So array of chars are interesting because we have something special in a string. In a string, we have an end of string character. So that means that we could here say, I want a function that's going to dynamically allocate an array of char. And you see how easy it is to go from from an array of int to an array of char. I just replace the data type of the element being referred to everywhere. I need to update also my prototype here. And I might actually want to change the name of the function because, allocate array of int when you allocate an array of char. This is not really helpful. This is downright misleading documentation right there. So I have my allocate array of char function. I tell it allocate for me an array of 4 characters, and then I can put values in that array. I can say, so I don't have to use the 4 elements. For example, I can say ptr index 0 equals h, okay? Ptr index 1 equals I. So that's going to be my message, hi. And ptr index 2 equal, well, since this is all for my message, \0. I could put something in ptr index 3, okay, for example, uppercase Q, but it's never going to be displayed. When I display a string, and I say this is ptr, and I use ptr here, so I give the address of the first element of the string, of the string of the array, it's going to display the h, the I, then encounter the \0 and stop displaying anything. Okay, so let's test that. Compile, run. There we go. PTR is high. The message that I'm displaying is high. If I wanted to iterate over this array, I could do it different ways. I could do it the same way that I did in previous videos with an index, I lesser than. So we're going to say lesser than 2 actually, because I have only 2 characters I want to display, and then I plus plus, and I'm going to do printf, and I'm going to get a little fancy. I'm going to put around the character like square brackets so that they show like separate one after the other, and a space after that on top of it, and I'm going to display, so I want to display ptr index I. Okay. And this is good, yeah, that should look decent on the screen too. Let's compile, run it. So contains the letter H, contains the letter I. If I wanted to display the content of the entire array, I would say lesser than 4, okay, from 0, index 0, 1, 2, 3. And that would display H high, the \0, which is not going to show much on the screen, and then it's going to show me that there is a letter Q. And of course, if I was careless, I would forget that I have only 4 elements here, and I would say, why don't you display, one element past the end of the array? And of course, C would try to do that for me, okay? And it would display whatever is in memory after the end of the array. What if I try to display a bunch of elements that are after the end of the array? Well, that would still work. That's the thing that's scary about the C programming language, is that the C programming language trusts the programmer absolutely. If the programmer says jump off the cliff, the C program is going to jump. Okay, no problem about that. So you have to be careful. You are the one that has to keep track of that, because what you are doing here is you are reading memory that doesn't belong to that array. So you could be exposing data that is in over variable in memory and displaying it even though you were not supposed to. And if you write to that memory, it's even worse. You could corrupt the value of over variable. So this is really like bad mojo there. Very technical term, bad mojo. So here we are going to do it correctly. We are going to stop at 4. We're going to display the content of the array. But if my goal is just to display what's in the string, okay, and stop automatically at the \0, then what I could do instead, I could do a while loop, and I could say int star p equal ptr, okay, while star p plus plus, and then I'm going to printf and printf. There we go. So what's happening here? Well, first, let's make sure that it works and compiles, so that I don't explain to you code that is full of bugs. In star from incompatible pointer type, yes, I think too much about ints, definitely in my examples. There we go. Let's do a char star here. Everything else should be okay. Let's go. Compile again. I is undeclared. Probably yes here. It's because I did a cut and paste, and I should have changed here star p. There we go. And actually the plus plus should be here. So I'm going to fix that. So on the same swoop. There we go. And here's what the swoop is doing. It's displaying h. It's displaying I. Okay. So why? What's going on? Well, it's because of this condition here. So first, it's displaying whatever is pointed at by p, so star p, the reference p, then it's increasing p. So if I wanted to write this a little bit clearer, not trying to fit everything in as few lines as I can, which is not always a good idea in terms of clarity of the code, I could say I increment my pointer after I display the character that is pointed by my pointer. So that makes it a little bit clearer. What about this condition? While star p, what does that mean? Well, star p is, again, the character that is being pointed at by p, right? So, whoa, how is that true? How is that false? Well, what we are doing here is we are writing while star p is different than \0. It just so happens that the index of \0 in the ASCII table is 0. So the character \0 is represented in a table, in an ASCII table, with the character at index 0. So when you write \0 between single quote, the compiler, you understand that it is index 0 in the table of character. The same way that when you write single quote lowercase a single quote, I don't remember the number, but let's say 64 or 94, this is going to be the number that is used actually inside your program, in the internals of your program. So here, what we wrote is, well, star p different than 0. Well, in C, everything that is different than 0 is true. So I don't even need to write different than 0. If I write while star p and it gives me something that is different than 0, this is going to be assumed to be true. If it gives me 0, then it's going to be assumed to be false. Okay, these are the rules for Boolean in Boolean values in C, in the C programming language. So we are using here pretty much, we are just shortening, I would say to the max, but there's probably a way to make it even shorter. I don't know. I have to think about it. But we are trying to shorten here as much as we can and turn this loop into a one-liner using all the dirty tricks that we can think of, right? And it's just exploring this array, this dynamically allocated array of char, and stopping automatically, not necessarily at the end of the array. We cannot do that without knowing the size that has been allocated, but at least stopping the first time we encounter \0. Okay, so we can dynamically allocate arrays of characters. We can go through them, and we can read. We can display, for example, every character until we meet the \0 marker of end of string. The next thing that we are going to do is we are going to look at a technique that is very, very common. When you have to read a string from the user, okay, you don't know, sometimes you don't know ahead of time how long the message that the user is going to type is going to be. So I can say, for example, printf, enter a name, and I'm going to say 5 character max. It's kind of weird, right, for a name, but doesn't matter. It's just to make an example. So printf, enter a name, 5 character max. How do I read that? Scanf, %s, and more specifically, %5s, okay? And then the name of an array of character, for example, name. And I don't put the ampersand because the name of the array of character is address, so I already pass an address to scanf. So here's char name of size 6. Okay, I'm adding 1 for padding for the \0. And there we go. I'm going to read up to 5 characters. I can store them in the array name. The last element of the array is going to be used for the \0 if I filled up to 5 characters. But if I type just hi, enter, right, it's going to store the h, the I, and then the \0, and the last 3 slots of the array are going to contain whatever garbage. We don't care. Okay, we're never going to go and look at them. So here, I did that with how to say, a variable that has how to say, statically allocated number of character here, 6. Okay, and I'm potentially wasting some room. Okay, so if, for example, if I say 100, 100, 100, well, the user can type actually up to 100 characters, okay? That's okay, and I'm going to actually have to do 101 here. There we go, just for the \0. So the user can type up to 100 characters, but what if I enter, on average, very short names? So I took 100 because it's huge, and I don't expect anybody to have, like, for example, a first name that is longer than 100 characters. That's why I chose this huge value. I could have chosen 1,000, okay, just to be safe, but to accommodate every user of my system, no matter how long their first name is, for example. But here's the thing. Once I have done this, then I store what the user typed inside of an array of characters that is 100, or even worse, 1,000, if we would have made it 1,001 element long. I store this little name like John, Jake, or whatever, Jane, and I store that in a huge array. So a lot of it is not used. The first few letters are there, then there is a \0, and then I have literally 100 of slots in my array that are completely unused, that are just occupying space in memory. So one of the things that we often do is we use the concept of a buffer. Okay, the concept of a buffer means that we are going to have this huge variable, for example, like 1,000 character plus the \0 can fit it. We are going to read something from the user, and we are going to allow it to be potentially very big. But then what we want to do is we want to make sure that after we are done reading this from the user, we are going to have another allocated piece of memory that's tighter, that's just big enough to accommodate the exact number of letters that have been entered by the user. How do we do that? Well, we are going to declare a pointer. We are going to allocate dynamically with Malloc size of char times a certain number, okay? And that number will be the length of buffer. So when I call strlen string length on buffer, okay, I don't measure the size of the entire array. I look at the array and I look at the first character and I count 1 character, 2 character, 3 character, 4 character. But as soon as I encounter a \0, then I'm done. Okay. As soon as I encounter a \0, I know I reach the end of my string. Therefore, I stop counting. For example, even if I have a huge buffer like 1,000 character, if I display strlen of that buffer, which I'm going to do right now just to illustrate it for you. Okay. If I say, for example, printf, your name is %d char long, and I'm going to display strlen of buffer. So you're going to see that it's not going to tell me 1,000, it's going to tell me the length of whatever name I typed. So it's aware of that \0 thing going on for strings. Well, that's why I'm using it here as well. I'm going to say I want you to allocate enough room to store strlen buffer plus 1 character, plus 1 for the \0, because the \0 is not counted by strlen. And once I have this, then I can copy all of the characters that I had in my buffer into the variable, the newly allocated space that is referred to by name. I can do that with a function called strcopy. We are going to talk more in our apprenticeship exercise about all of those functions that are available to manipulate strings, okay? But for now, I'm going to do it by hand. I'm going to say char star p equal name while star p, and I'm going to say that what I want to do is star p equal buffer. This is where I want to read the data from, and star p is going to be equal to buffer, and I'm going to just do buffer plus plus and star p plus plus. Okay, so again, this is a shorthand version, but we're going to like first compile, debug this code, and then I'm going to show you exactly step by step how it's working. Okay, so I need to do some output here. So I didn't save my file, didn't I? No, I didn't, of course. So let's compile. That's better. Well, it's not better, but it's more expected. So strlen is not built in. So you need to include include string.h. It even tells you in the error message. Ah, nice. Save that. So let's get rid of that bug. Go to the next one. Format %d. This is me again using ints everywhere. Where I should be using something different. Yeah, there we go. So this is going to be a size. So it's going to be %zu, just like the size t data type that we have used. F value required. Yes, I cannot do that, can I? Yeah, I'm trying to increment here the name of an array. So this is not going to work. I'm going to have to use an index. You know what? We're going to do it even sneakier than that then. Star p source is buffer, and then char star p destination equal name. Okay, so what I'm saying is that I'm going to read the character from buffer. I'm going to write them in name, and then now, so this was completely wonky, so it's a good thing that I have to rewrite it. While star p source, I'm going to say star p destination plus plus equal p source plus plus. Star p source. There we go. Save this. Compile. Run. So I can type up to 1,000 characters. Let's start small. Hi, your name is 2 characters long. So yep, strlen is going to measure the length of a string as the number of characters before the \0. Then I allocate dynamically my name. I don't know how to refer to that. Allocate dynamically a space in memory that is big enough to hold exactly 3 characters, 2 characters for H and I plus 1 for \0, and then I copy everything from the source to the destination, and at the end I must remember to do p destination equals \0. Okay, so how is this going to work? This is a part that's interesting. Okay, so we are going to trace that on paper real quick. Let me grab an eraser. There we go. Clean this up a little bit. So how does this part of the code work? So first, I have buffer. Buffer is a regular array, size 1001 element. Okay. All right. I have this. What else do I have? I have ptr, but I don't think I'm using it in this version of the code. No, I'm not. I have name. Name is just a pointer. Okay. And name, I allocate here a piece of memory. So in my example, I'm going to consider that I'm entering high. So here's what's inside buffer, h, high, and then \0. Okay. And then everything else is, I don't care, it's garbage. Okay. There are characters here, there are slots for characters, but I'm not using them to store my string. This here is going to be exactly 3 character long. Okay, this is what I do on line 17. I allocate an array of 3 characters, the strlen of buffer, which is 2 plus 1. And then I have that p source, which I'm going to abbreviate p underscore s, okay, which is also a pointer on char, and that pd for destination, which is also a pointer on char. ps is pointing to the first element here in buffer. P destination is pointing to the first element here in the array that was dynamically allocated. And what I do is while star p source, so p source is here, star p source is here. So while the character that is pointed at by p source is not \0, that's what it means, keep iterating inside this array, keep increasing p source. So increasing p source means that I'm going to point here, then I'm going to point here, and then I'm going to bump into the \0. Okay. Same thing for destination. I'm going to keep incrementing the destination here, then here, and at every iteration, what I do is I say p destination. So this location is assign the value from the corresponding value from p source. Okay, and then I increment here. I increment here, and I assign this guy to this location here. Then I increment again. I increment again. And then I realize that I met the \0, and I stop my loop. If I stop there, this is why I added line 22. If I stop there, there's something missing here. Okay? This here is not a \0. That means if I try to printf that string, it's going to display the h, the I, whatever is here, which I never set, and then it's going to keep going displaying everything in memory until it meets by just fortitude, until it meets a \0. So instead of doing that, letting that happen, I'm going to say star p destination is \0. So here I am replacing this by actually a proper end of string marker. There we go, \0. And that's how it works. So this is I didn't try to sugarcoat it this time. So I went directly for the compact version. You can try, if you have problem understanding that, you can try rewriting it in a more, step-by-step manner instead of trying to make your loop, one line, like line 21. Write it in a more expanded version. But make sure that you understand how this copy operation works, okay? Because we are going to re-implement anyway the function strcopy, which is part of the string.h library. We're going to re-implement our own version of the basic string manipulation function, starting this module, continuing next module. But it's really important that that you know how those are working internally, because they are probably among the best example of work with pointers that we can use at our level. Okay, so here we have allocated dynamically a tight-fitting area of memory, tight-fitting meaning that it's just big enough to store the name. And when I don't need it anymore, I can deallocate it. So I can deallocate, in this case, name. I'm going to remove that PTR because I'm not using it at all anymore. There we go. Buffer, I don't need to deallocate it because it was not dynamically allocated. Okay, it was statically allocated, and that's it. And p source, p destination, there was no malloc operation with them, so I'm okay. I just use them as pointers, to follow inside the arrays. So that's it. We have pretty much covered all the basic operations that we can do with arrays and pointer. The one thing that's left, but I'm going to detail it in the examples, in the reading assignment, and in the exercise, is what if I allocate dynamically an array, but each element of that array is itself a pointer, a memory address. And then I can go ahead and allocate dynamically strings. So we are going to look at that, but in the context of exercise and examples in the reading assignment. All right, that's going to be it for this already long video. As usual, thank you for your attention. Don't hesitate to use office hours, post on Piazza, forum, whatever we use this semester, and I'll see you in the next video.